All right, let's now look at the reminders as usual, and then we talk about your bridge controller. Your programming test number 1 and written test number 1, the result and the feedback have been released. And if you haven't noticed that, for your programming test 1, I also released the test questions, solutions, and also your original submission files. Take a look at them, dive deep, and then if you want to go over any parts together with me, just drop by or make an appointment. And then this may not be just useful for your upcoming, I would say this may not be so relevant to programming test number 2 next week. I'm going to release the practice test to you. That one definitely is going to help. But you want to make sure tomorrow, October 30th, make sure if you got any struggle through lab number 4, make sure you show up to any of the session, either 1:30 or 2:30. So Andy, our TA who helped me design the lab number 4, he is going to be in the lab session tomorrow. So just make sure you come if you got any question. And Andy plans to do the demo for your lab number 4, just to show you how you can walk through all the prover steps on rodent. So if you got any question, you can just interact with him during the demo. He's going to do the same demo at 1:30 and also 2:30. So you can definitely just go to one of the sessions or catch him afterwards for questions. He doesn't come to campus often, but he will be here tomorrow just for you guys. All right, so please come if you need help. And your lab number 4 is also going to be due on Friday. But I would say if you follow through all the steps, and then all you got to do is submit the exported project. That's all I expect. And then just make sure you can do the proof of step next week in the programming test number 2. All right, so that will be the plan. All right, do you guys have any questions about the course? Yeah. Are you talking about programming test 2? Are you asking about what it is about? Yeah, so I'm going to release the guide tomorrow. Programming test 2 basically will be very much like your lab number 4. So there will be 2 parts. Part number 1, you're going to do some formal specification, like a part 1, pretty much like a programming test 1. But that will be a little bit shorter. But the main part is going to be part 2. Part 2 will be like a part 2 for your lab 4, where you're going to do some proofs. But the difficulty for the proof will be just similar to what you do in the lab, very similar. And tomorrow I'm going to give you some practice questions, and then if you practice them, it should be okay for the actual test. Yep, you can see, you can look forward to it. I'm going to release the information tomorrow, or early Thursday, the latest. Okay. All right, guys, any other questions about the course? All right, and again, if you really want me to go through some part of your questions on the test, feel free. I still got office hour this week on Thursday. And tomorrow, I'm not exactly sure if I might be available during the scheduled lab session time. If you see me around the lab, just drop by. Okay, you can catch me. Otherwise, definitely Thursday. Okay. All right, let's now do a very quick recap about what we talked about yesterday. Things are getting more and more interesting. So we are really trying to use the mathematics to help us build a bridge, somehow to improve the model. We hopefully will see some example today. But let's just see what we said last time. So last time we were still paving the ground to really make sure all the formal components in the proof obligation rule can be understood when you look at them. But we're going to see more today. So we talk about the informal sketch for invariant preservation. I would say this page over here was only just to give you some intuition. But last Thursday, we already started the formal components in the proof obligation rule. So now it shouldn't be too bad for you to see it. Right, this page here is really all the components you're going to see for most of the proof obligation rules that we need for this course. So I would say whenever you kind of forget about, for example, what AC or GC really mean, you can always come back to this page to make a reference. And then let's now take a look at this one here. All right, so that's a sequence rule. So this is our first proof obligation rule for invariant preservation. Every time you see a proof obligation rule, the number one question you want to ask yourself, how many sequence can I really generate given the particular model we have? For example, given this particular model here, you can see we got 1 and 2 events. We got 1 and 2 invariant conditions. So this one kind of tells us when we look at this proof obligation here, for the G here, that refers to the guard of some events, which can be either this one here or this one here. So we already got 2 possibilities. And then when we look at the I here, and notice that it's being indexed over here, I. So whenever you see just the I itself without the indices, that refer to the entirety of the invariance. But if you see some index over here, that refers to individual, for example, 1 or 2 of the invariance. So now in this case, we can have 2 possible guards, either the one for ML out or the one for ML in. We also got 2 possible conditions for the invariance. It could be either condition 1 or condition 2. So if you multiply these 2 dimensions together, we got 2 times 2, so 4 sequence in total. So the easiest question you can expect, maybe later, is I give you a particular model, for example, like this, and then I give you this proof obligation rule. And now I say, generate all the possible sequence that's implied by this particular rule. Right? That's a typical question you might have. Do you guys have any question about how to look at individual components over here? And also to work out, we need 4 in total. The combination between the 2 guards and also 2 invariant condition, which would be what we said last time. We got ML out, ML out. If you look at the slides, I can also show to you. If you haven't done the exercise, I would really highly recommend you try to really generate yourself. But if you go back to the slides, that's what you will see. Let me show you. If you go to the slides, you can see that over here, slide 19, this one shows to you 2 of them, ML out, either with invariant condition 1 or invariant condition 2, right? That's 2 of them. I believe later in the slides, you will also see them. Let me go ahead a bit just to show you. Okay, sorry, just a little bit ahead. This is something we'll talk about today, but I just want to show to you the invariant condition. I should have put another page over here, but anyway. Okay, how about this? I'll show you on the page very quickly. Yeah, this is a really fundamental step. You want to make sure you know how many sequence you will need. Otherwise, you wouldn't even have a clue, like which one to prove. All right, so we already got these 2, and the other 2, let me show you ahead on my notes over here. You can see exactly here. All right, so these will be the 4 we're going to look at today. We got ML out, ML out. ML out can be either associated with invariant condition 1 or 2. Symmetrically, we also got ML in, which can be associated with condition 1 or 2. And the nature of these 4 are to do with invariant preservation. And what we're going to do today is to see how we can discharge these 4 sequences. If any sequence that we cannot discharge, it might suggest some problem in the model, which requires some fix. So this one is a little bit like when you develop your Java projects. You write some JUnit test cases, run them all. If you see a green bar, that's great. If you see a red bar, there might be something wrong in your code. Go back to fix it, rerun the JUnit test cases, and get a green bar. That's something we're going to do as well. We try to prove all the sequence first at one go. There might be some sequence that's shown to be unprovable. And then based on those sequences that's unprovable, we'll go back to the model, fix something, regenerate all the sequence, and try to discharge them again until we can discharge them all. That's kind of the process. All right, let's go back here. And then there's one more bit to recap. And then we should be ready to do the new stuff. All right, so we got all these 4 sequences you want to generate, 2 times 2. And then one of them would look like this. All right, you're just going to put, for example, axiom, all the invariants, and one guard condition, in this case, the guard for ML out. And then this one here, you're going to kind of separate them. So put this one here into here versus this one over here into here. So they are separate sequence. All right, so we only try to prove the goal condition one at a time. We don't try to combine all the invariants together because in practice, you may get many invariant conditions here. You don't really want to prove them all at one go. That's too complicated. And one more thing to say, the way to work out this goal over here, if you look at this part here, is about the invariant condition being satisfied at the post states. And this E here, you can go back to that components page. This refers to the effects of the event action meaning that the before-after predicate. So you have to look at the before-after predicate for the events. And once the intermediate step you can try is to, for example, let's say this invariant condition. I simply put it here and put a prime in all the variables. So this really tells me this is the predicate, m prime is a member of natural number, tells me what should be satisfied in the post states. And then I'm going to work out exactly what m prime is in terms of the pre-state value. The only way I can work this out is go back to the event action over here for m out in this case. And then I can see the becomes operator, colon equal to. Again, try not to think of it just like a variable assignment. You can easily fall into the trap of sequential composition. Right? That's kind of the swap specification we talked about earlier. And once you look at this, you will know that the corresponding before-after predicate is m prime equals m plus 1. So now we can safely substitute m prime over here just by m plus 1. That's why ultimately you'll see m plus 1 is a member of natural number. So this might be the trickiest step you want to get right. And this expression here is actually not that complicated to do the replacement. Later on, we're going to see the more complicated expression. But the substitution is going to be similar, following the same principle. So guys, specifically, are you OK with doing this with the intermediate step? Just make sure you're fine. All right, if you got trouble, that one is really something you need to get help first. I remember when I taught earlier this course, I think usually in the beginning, students usually suffer the most from working out exactly this. But we're going to see many more examples, right? So I'll try to emphasize that more. All right. So this is where we ended last Thursday. So I would like to recap a bit, and then we can build on top. So this is a new syntax we have to learn for this course. We learned about sequent, which uses turnstile. I might say something turnstile this. I might say something turnstile this, either way. But now for the inference rule, you only got one option, right? You got to put a horizontal line. Above, you have a set of sequence. You don't have a set of predicates, a set of sequence. And below, you have a single sequence, only a single one. And the interpretation is, this is something I can start building on top. So the way to interpret this goes like this. And it's a simple definition you have to remember. Of course, later on for the exam, you will be allowed to bring a piece of data sheets. You can also put this definition down, just in case you forget. I'll talk more about your data sheets later. Okay? So how do we interpret this? To prove the consequent C. It is sufficient to prove the antecedents A instead. So the instead over here is really important. So that means you can feel free to, rather than proving C, I can choose to prove A instead. Because proving A will be sufficient to argue that I have already proved C. Right? That's kind of the rationale. So this will be the simple definition you want to really remember. All right? And then, of course, you can see the C here and also the A there instead. And when I say instead, that means we can feel free to rewrite. There will be quite a bit of rewriting. And proof effectively is about rewriting in a sequence of steps, which we'll see definitely some example today. Rewriting. And the example I also gave to you last time was, let's say we got this. This is an inference rule. So this MON corresponding to L is a label. So it's called so-called a monotonicity rule. That's just the name. And this part over here is a single sequence, C. And this part here is just a singleton set. Well, it's a set with only a single sequence over here, and that's A. And the way to interpret this is saying if I have a sequence with a goal to prove G, I got two hypotheses. I want to prove this. However, if I like, I can choose to prove the following instead. It would be sufficient for me to prove H1 only as a sequence by dropping H2. Let me repeat. In order to prove this particular sequence with hypotheses H1 and H2, I can, based on the rule, choose to prove this sequence instead. That sequence in some way is simpler because I can choose to drop H2 and then just prove H1. So now I will be able to, if I can prove that, given H1, I can show G being provable, I can conclude, given just some extra hypothesis, of course, I can also prove G. Question? H2? Over here? No, we don't need to. Sorry, say it again. I don't quite catch you. Okay, so in this sequence over here, we want to show that G is provable, given two hypotheses, H1 and H2. But now, if you decide to say one of the hypotheses doesn't seem to be relevant, I can drop it. So let's say I don't really want H2, I drop it. So instead, I try to show to you H1 can show that G is provable, that'll be enough. That's what it is saying. Yeah, we'll see example. Okay. This monotonicity, don't worry, you're going to get very familiar with it. That one there is going to appear almost in every proof, almost. Because normally what you will have is you got a lot of hypotheses for your sequence as a proof obligation. You don't really find all the hypotheses relevant for your proof. So you should really drop all the irrelevant ones first as a first step. That's what's going to happen. And let me make a note here. We can see. So this monotonicity here informally is to say you can drop hypotheses. If you are given two hypotheses, you can drop either H1 or you can drop H2. All right? That's good for now. And then let's now go over a little bit slides, and then I want to show you some example proof right away so you can get some idea about how a proof can look like. All right? So that's something we should do. And, okay, good. Before that, let me just say one more thing, since there's a question here. Similar to the sequence case where, if you remember, if I got a sequence, let's just go back to turnstile. If I simply got this, and then I got some goal over here. We say that this will be as if you say true, and then G. Right? This is something we spoke about before. So now we got a similar situation to consider. Let's say, what does it really mean when A is empty, meaning that we don't have any antecedent? How does it look like? It looks like something like this. If I have, let's say, some inference rule over here, I don't have anything above the line. I only got some consequent over here. That's it. This is the inference rule, which we're going to see quite a lot. For example, let me show you one of them. This is an inference rule where you don't see anything above the line, only something below the line. This is to say, to prove this sequence over here, it would be sufficient to prove something that's empty. But what's really empty? That means you don't need to prove anything. That means it's automatically proved. So should we put true here or false? True, because true is automatically proved. Okay, let me say that again. So this sequence over here tells us 0 is a member of the natural number. In order to show that this sequence here is provable, it would be sufficient to show that true itself is provable. But it's automatically proved because true is always provable. All right? Yes? Say it again. it's basically an axiom. That's something I was just about to say. So the way you can interpret this, for example here, by the way, the P here stands for piano. So I'm not sure you heard of piano number theorems. It's actually some famous mathematician. But if you haven't heard of it, that's fine. So P1 over here is one of the axioms. So whenever you see any inference rule where above the line it is simply empty, that suggests whatever we put over here is automatically provable, meaning that it's an axiom. So that's a remark you just made. All right, so now let me go back here and make the notes, and then we can move on to some example. So this one here, when we simply got nothing above, this will be just the same. Some label means true is above the line, and then we got C, meaning that C is an axiom. There's no need to prove it. No need. All right? Well, if you want to apply the definition, in order to prove C over here, it would be sufficient to prove true. But true is always automatically proved. So that's why nothing to prove. All right? All right, now let's move on. But before we move on, you want to make sure you kind of remember the inference rule and also the label. We're going to see lots of them. And also the, for example, we're going to see that. Maybe one more comparison, if I may. So far, we have seen two syntax. It's good to put it in one place and then make sure we don't really get confused with them. We talk about sequent. And then we talk about inference rule. They are closely related, but they are not the same. Okay? For sequence, it can be, for example, some hypotheses, and then show that the goal is provable. And for our proof, normally we try to box them, normally, but you'll see some example proof. And the semantics for that is H implies G. All right? And then we say that this will be a set of predicates. This will also be a set of predicates. Okay? That's sequence. And for the inference rule, what we have is a horizontal line, and we got some antecedents, and also we got some consequence, right? And then we got some label. Normally, for the sequence, we don't have a label. That's already some syntactical difference, okay? And the semantics for that would be A implies C is equivalent to true. And the way to understand it would be, in order to show that C is true, it would be sufficient if you just show that A is true. And normally, we want to rewrite C into A. That's something you will see later. Given this rule, that means to make progress in your proof, rewrite C into A. And the rewriting should really keep happening by keep applying inference rule until you reach some axiom inference rule. So the step is actually summarized in the slides. Let's go over a little bit bullet points, and then I'll show you one example. And then we go back to the bridge controller. All right, everything here. I'll go to this example in just one moment, but let's now see the steps. So let's say this is some proof, some sequence you want to discharge, right? You want to apply some inference rule. You want to transform this sequence into one or two more sequence. And then the idea would be you want to keep applying the inference rule until you don't really require any further justification. So number one and number two here really summarize about how we should proceed with the proof. That's the kind of the idea, okay, big picture. And let's now do one proof together. Okay? This one here. This is one of the proof obligation that we just generated. it is the invariant condition, preservation, invariant condition 1, and we want to make sure with the effects of ML out taken, we will be able to preserve the invariance. And that's the sequence, right? That's something we spoke about. All right, this one here. Currently, it is outstanding, unless we show that it's provable. And for this one here, we actually got 1 and 2, relevant inference rule. So for the purpose of the in-class illustration for our discussion, normally, if we got any outstanding sequence to prove, to actually save our time, also give you more guidance, normally I put only the relevant inference rule over here. However, the challenge for you in the written test number 2, and also the exam, is you will be taught maybe about 20 or so inference rule, and then whenever you are facing an outstanding sequence, you have to work out exactly which one should be relevant. Right? So that really takes some practice and also creativity. You got to try different paths, right? Pretty much like how you did proofs in 1090. So the proving process itself is really hard to really teach thoroughly. I can just give you some example. Sometimes I'll show you some, share with you some insights about how I thought that should be done that way. All right, so now let's take a look at this one here. How do we discharge this? So this will be our very first proof. The idea would be, given this one here, we want to somehow rewrite this sequence in a sequence of inference rule application until we reach a single sequence, and that single sequence is already an axiom, and then we are done. All right? Let me start you with the following. Let me start by copying this on the leftmost side. Okay, this is our starting point. Most of the time, you're going to need monotonicity. You want to somehow decide which hypotheses might be more relevant for proving the goal. That's the first step. All right? So now we know that the goal over here, which I'm going to highlight in orange. So you can think about this guy here, it's like the G. All right? That's what we want to prove. And by the way, whenever you want to apply inference rule, it's more like a matching the pattern. So you can see the pattern over here is really the G here. Right? That's why I'm trying to highlight that carefully. And at the moment, you can see here we got 1 and 2 and 3. 3 different conditions for the hypotheses. And we can somehow divide them into H1 and H2. That's a general one. The order doesn't really matter. As long as you can somehow say some of them belong to H1. For example, this might be H1 and this might be H2. In that way, I will be able to rewrite this by dropping maybe H2. Or if you decide this will be H1 and this will be H2, in that way, you can drop these two. Also, that's possible. Right? You just got to decide which one should be H1 and which one should be H2. And for this one here, I'm going to tell you which one. Okay? That's your first example. I would say the blue one, I'm going to highlight this guy here and this guy here. These are not as relevant. They are going to be dropped. So I'm going to call them H2. All right? Of course, in the actual proof, you don't need to do this, but for now, it's your first proof. I'm just going to show to you. Let's say this is H2. And the remaining hypothesis is going to be H1. So think about this is like H1 and H1. Let me emphasize again. There's no magic here. I know the solution. That's why I can kind of explain to you in a way that's going to make sense. But when you are facing a new proof, don't really expect that you will be able to work out a perfect proof at the first go. You may have to do trials and errors. That's normal. The same for me. All right, there's no magic here. But let's say for this one, the way I judge it is by looking at, because somehow I want to know whether n plus 1 is going to be a member of the natural number. So apparently, I need to find out something about n in the hypothesis. In that case, this one is not very useful. That's about d, and nothing to do with n. And also, this one here might be useful, but somehow I only say n plus 1 But what does it have to do with D? D is also nothing to do with N. So that's why I can also drop it. Right? So that's kind of that's kind of question you want to ask yourself, which one to drop. All right, after identifying the G, H1, and H2. Okay, so this one here is G. Now let's now recall this rule again. This one is telling us in order to prove this sequence over here, it would be sufficient to prove this sequence instead. This is where the rewriting is going to happen. So the syntax we're going to follow for the rest of the course will be, now if I want to rewrite this sequence, what I will do is I'm going to say the rule I apply, which will be monotonicity. All right? And then on the right-hand side, I'm going to put something that's going to correspond to this guy here, the sequence above the line. That one there is going to be just H1 entails G. Okay? I'm going to write it. And H1 is just N is a natural number. And then I got here N plus 1 is a natural number. So this is your very first proof step, and that's very fundamental, right? It involves basically everything you're going to need to apply later for different problems. Let me repeat very quickly. You're given something here to prove, and normally you will only give, the sequence will normally only have one condition here. So you want to look at this condition here and try to see what's the relevant variables. And from those relevant variables, what kind of properties do I really need in the hypothesis to help me in the proof process? And for those relevant ones, I'm going to keep them. For those that may not be so relevant, I discard them by using the monotonicity rule. Of course, later in the proof, you might find that I may have dropped the wrong hypotheses, which I might need it. Just go back, backtrack, and come back to add them back. Okay? And I'm going to write this one just for once, just to remind you about a thinking process. So, analyze the goal predicate to prove. What are the relevant variables? In this case, only N. What are the relevance variables? All right? And also, what hypotheses are useful? For me to actually prove it ultimately, you need to have some general intuition, right? Relevant variables and what hypotheses are useful. These are the two big questions you want to ask yourself every time, okay? If you're lucky, you just drop the right hypotheses, you might just end up having the right proof, right? All right, so now let me also try to make sure I also box this sequence over here, right? It'll just look more like a neater over here. All right, so we basically go from sequence number 1 to sequence number 2, just because in order to prove this sequence over here, it would be sufficient to prove this one here instead, which corresponds to this. All right, so when you go back home today, or maybe tomorrow, you want to really look at this example here, really convince yourself we are applying the rule correctly. There will be many rules to come. All right, hey guys. Now that you got a little bit of experience, why don't you take a look at this sequence over here? We are not done yet, because just this one alone, we cannot really say that's automatically an axiom. Not yet. This one is to say, I want to, given this hypothesis, n is a natural number, n plus 1 is a natural number. It sounds right, but do we have any axiom to support it? So, when you look at P2, are you convinced I can directly say, given P2, I can conclude this one here is proved? I'll give you 1 minute. Take a look at this sequence over here and this rule over here. And then I'll explain. Okay? Take one moment to really think about. That's basically what you got to do. What we're going to do in the lecture and what you got to do in the test. Okay, one more moment, and then I'll explain. Okay, so if you look at this inference rule, that one there, you can see the above the line is empty. So that means in order to prove this, we don't need to prove anything. It's automatically proved. So this is an axiom, this rule. And does this rule really match this entire thing? It does, right? Let's see. The only difference is this is vertical. This is horizontal, if you can see that, right? Let's now make sure we are okay. So this one here, you can see n plus 1, a natural number, n plus 1, a natural number, n is a natural number, n is a natural number. So you can think about this whole sequence here just correspond to this whole sequence here below the line. And this rule tells us if you got a sequence like this, you don't need to prove any further. It's proved. So the only thing we got to write is to justify this step by saying P2. And that's a proof. This is something you want to get very used to. For written test number 2, you will be a little bit better because you will be given multiple choice to let you kind of organize the sequence. But in the exam, you have to write such proof yourself. But you still got time to get used to it. Okay. This example here also suggests one particular proof pattern you might have. Okay, let me show to you. Just summarize right away. You might start with something here. This is your beginning outstanding sequence. And then you got some turnstile over here, and then you have some goal, a single predicate you want to prove. And then you simply got so many hypotheses, some of them relevant, the other ones irrelevant. Typically, the very first step is to really make the hypothesis list much shorter, shortened to only the relevant ones. And then once you got monotonicity, you still got G here, and then you just got maybe a few left. And once you got to the maybe the minimum possible hypothesis list, you're just going to apply a sequence of rules. And for example, you might say, I'll just say R1, R2, right? Just make it up. You might do R1, in which case you can go into a sequence. You might do R2, that go to another sequence, keep going until you reach a case where that sequence there simply match some axiom rule. That will be the general structure for one particular kind of proof. And what am I missing here? The only case we haven't really seen, which you might see today, either today or maybe Thursday. You might think intuitively, I simply go from one sequence to another. But sometimes it might turn out it could be more like a tree. If I want to discharge this particular sequence, and let's say I apply certain rule, that rule might allow me to go to split this sequence here into two so that I can discharge them separately. And each one of them is going to be a branch of the tree. That's the missing one. But that's something we'll see later. But you can kind of see the idea. Right, so this will be the proof structure. That's the most straightforward one, which we're going to see mostly today. Okay, so that's kind of the proof steps. And R1, R2, like here, so these are so-called the recursive case of inference rules. Because it's not really ended, it has not ended just yet, right? It's not proved. On the other hand, the last one, like axiom, inference rule where above the line is empty, so this is more like a base case. Like a recursion idea of inference rule. All right? All right, any question here? All right, so I think this is really good because now we kind of have an idea about some very basic proof. I would say to really discharge all the 4 proof obligations that we just saw earlier in the beginning of today, this kind of proof structure here will be sufficient. That's something we should practice more today. And we're going to see the more complicated one maybe on Thursday. Let me watch all the time. Good. Okay, let me do one more thing and then we can take a short break. So this will be your first set of rules, all right? So we're going to look at one by one, okay? And I'm going to also post this as a PDF for you. You can feel free to print it out, load it to your iPad, etc. I'll leave it to you. And in the final exam, you can also put them on your data sheets, all right? That's no problem. And also another good news for you, we don't really expect you to, well, if you really talk about what are the possible inference rules, there are many. Possibly hundreds. But for this course, on the exam, we're only going to test you on the ones we show you in the class. Okay? More to come. Why don't we look at the green ones? The green ones over here, you can see the characteristic for each one of them. They simply got the antecedents empty, meaning that these are the terminating case for the proof, each one of them. If you somehow can show that you rewrite your original outstanding sequence from the leftmost part here, all the way to some sequence over here that simply match any one of these, you're done, basically. And the red ones over here are the recursive cases. These are for you to rewrite the intermediate steps from one to another. Let's not go over one by one. So let's now do the P1, P2, and the one I mentioned before. You can feel free to go to Wikipedia, look it up, optional. So the P here really stands for piano. Numbers theorems. That's why they name the rules after P. That's why. Piano. P-E-A-N-O. Okay? And the first one here is to say you don't need any hypothesis. It is directly provable. 0 is a natural number. Obvious. All right? This one's easy. Done. And piano theorem number 2 tells you if you know n is a natural number, then it follows n plus 1 is also a natural number. Obvious. This one here, I'll get to maybe this one here first. If I got n is a natural number, n should be larger than or equal to 0. By the way, this might sound a little bit familiar, right? One of the axioms that we did in Euro Labs 1, in the bank example, in the context, was actually using this one here. Anyway. All right, so P1, P2, P3 are all obvious. And let's now go to the less obvious one, which is not too bad. How about this one first? If I got n larger than 0, if you want some visualization, let's do it. Let's say this is actually 0. If I know that n is strictly larger than 0, the smallest n will be over here. If I say n minus 1, it will be at least still 0. So it's still a natural number. Right? That one also makes sense. And we got 2 more. These 2 are a little bit trickier. We got something called increments. We also got something called decrements. Okay? So these are also 2 rules we can use. And let's visualize them very quickly. The increment rule tells you if I got 2 numbers n and n, the hypothesis, n is strictly less than m, strictly less. And if I try to do n plus 1, n plus 1 over here, the most I can get will be just m. I cannot go above. Right? That makes sense, right? Plus 1. Because if I say n less than m, the largest n I can get will be n is exactly m minus 1. In that case, m plus 1 will just give me m. Right? Think about it. It's not difficult. And similarly, if I got this one here, if I got n is less than or equal to m. That means it can either be that n is strictly less than n, in which case n minus 1, of course, will still be less than n. That one's obvious. But what if n happened to be equal to n? If n happened to be equal to n, in that case, n minus 1, of course, it will still be strictly less than n. Right? Just talk about two cases. So the way to understand this rule is always think about when you got this one here, less than or equal to. Right? I'll make a note here. That means n less than n or n equal to n. If you consider these two separately and think about the goal, it makes sense. All right? Question? Sorry, say it again. Which?
What's the domain for n and m?
Oh, what's the domain? They're just numbers.
Okay, so
Like an integer. How about that?
so it has to be integer a?
Integer, yes. Okay. Yeah, not real number. We don't talk about real numbers in this course. Okay. Just, yeah. Mm-hmm. Yeah, so where the context is not exactly explicit, that means we assume they're numbers. Mm-hmm. Of course, if we say explicitly they're natural number, we are eliminating the possibility for negative numbers. Yeah. All right, guys, any questions about the axiom rule? All right, let me do one more annotation, and then we should move on to the slightly more complicated one. I want to explain them very clearly because later ones will follow similar convention. So this set over here is the axiom rule. Oh, that's pretty good. These are the axiom rules. Base case. And we're going to look at individual one by one. And let's now look at the most complicated one first. All right? This one's fun. All right? This one here, I'm going to discuss it separately. Okay, here. Let's not worry about proving it. But let's just understand what it is trying to say. I have a question for you. Number one, to help you understand. Does ORL, I'll make a multiple choice for you. Help us. Option A, split one sequence into two. Option B, collapse or combine two sequence into one. You might think this sounds confusing, but that's exactly confusion you might run into. That's why I want to clarify. Based on this rule over here, should we choose A or B? Option A tells us we're given one sequence to prove. Instead of proving one, we're going to prove two instead. B tells us we got two outstanding sequences to prove. Somehow, conveniently, the rule can let us prove just one sequence instead. B sounds better, no? Maybe I'm trying to be misleading you, right? Anyone? A or B? You think it's A. Well, how come do you think that should be A?
Because the original statement is H period shows R, right?
Below the line.
Yeah, below the line.
Exactly.
So
Mm-hmm.
it doesn't make sense for B if it's combined because then there's room for doubt.
Mm-hmm. Exactly. So basically over here, what I just said over there about being more convenient, I was just saying that to mislead you. All right? So if you basically want to remember this, right? The same principle. The way to interpret any inference rule, I'll get to the naming convention in a moment. It is to say to prove the bottom, it would be sufficient to prove the top. So this one is to say, if I want to prove this single sequence over here, it would be sufficient for me to prove the above. How many sequences do we have above the line? 2. 1 here and 2 here. Let me visualize that a little bit more. Okay? So this rule tells us if you got a sequence like this, I got R to be shown provable. And then I got 2 hypotheses. I got H here, I got P or Q over here. Right? You want to convince yourself this guy here is just the same as this guy. At least you want to see that, right? Okay? This rule tells me if I want to show that, if I want to prove this sequence over here, it would be sufficient to prove this one and this one independently. Okay? So now, by the rule of ORL, again, I'm going to explain the naming convention in just one moment. It would be sufficient for me to prove, normally we just put some bracket like this. All right? And then I'm going to prove number 1 here. So this will be the left sequence, for example. H, P, turnstile, R. So this will be the first sequence to prove separately. And then this will be the second one. And here this will be H and Q in tells R. All right, so option A is really the answer. But I want to keep option B there so that you know that that one is not really the case. Okay, option A, that's the correct one. Okay. And let's now compare this pattern here to really fully understand it. The goal that we want to show provable is R. So R should still be here. You can see somehow you got a single sequence to be proved originally. Even if you split into 2 sequences, if for each one of them, the goal will still remain to be R. R doesn't change. What really changes is above the turnstile. It used to be that we want to have the hypothesis H and P or Q. So now H is still there. So H here, and H here. They're still there. The only difference is, you can see now, we used to say P or Q as a disjunction. Now we can say you want to somehow prove that if P alone is enough, and also Q alone is also enough. All right? So now let's see here. P here, P here. Don't worry, I got many colors. Q here, and Q here. All right? You can see all the correspondence here. All right? That's how you understand the rule. Okay, and then we just got to use it. Okay, so let me explain the convention here. Number 1, you will see that there is the L here. So the L here tells you the rule concerns what's to the left of the turnstile. L stands for R. So you might see something about R, which is right, in which case we are doing more about the right-hand side of the turnstile. So the L here tells you which side of the turnstile you want to focus on. In this case, we want to focus on the left-hand side, in which case we're going to split P or Q separately into P here and Q here. All right? That's the L. And of course, the OR over here is just about the OR over here, right? That's obvious. Disjunction. All right? That's obvious. All right, any question here? I think for now, let's not try to read too much into the rule. You can think about it, because later on, we'll talk more about the comparison. Later on, we're going to see, you might be wondering right away, if we got OR over here, do we have N? Yes, we do. But somehow the N, the only rule we have, the N doesn't appear to the left. It appears to the right. All right, that's something I will compare, maybe a little bit later, okay? All right, I'll get question? Okay. And let's go over, maybe finish these, and then we'll take a short break. All right, we're done with this. And let's now talk about these two. And this one has been talked about already, monotonicity. All right, these two. And we still got OR over here. That means we are talking about disjunction. And now we see R here right away. R means to the right of the turnstile. All right? So that means to the right of the turnstile, we have some disjunction for us to consider. So let's now see R here tells us that it is to the right. To the right of the turnstile. So we are talking about the disjunction over here, and also we talk about the disjunction over here. And they are simply to the right of turnstile. That's how you read the convention, right? It's logical, but you just have to get used to it. And what about 1 here and 2 here? They simply mean operand number 1, like left operand, versus operand number 2, the right operand. So for the 1 here, we are basically focusing on the P. For the 2 here, we're focusing on the Q. All right? And for example, what does this say? This tells us if the disjunction happens to the right of the turnstile, meaning that you want to prove some disjunction. In this case, you can choose. Either you want to prove just P or you can just prove Q. Doesn't matter because it's disjunction. On the other hand, if you got the disjunction as part of the hypothesis, in that way, you cannot be selective. You have to somehow split them into 2 sequences and prove them both, right? That's the difference, okay? So if you look at this one here, R1 tells us, so now if I got, let me also get these two visualized for you. Let me do one more, and then we should be good to do more example after the break. All right. So this one tells us if you actually got H, P, or Q. This, let's say this is the outstanding sequence. It would be sufficient by ORR1 to prove we keep the same hypothesis, but now we only want the left-hand side over here. Just try to prove about P. That will be enough. That's what the rule is saying. Symmetrically, this one tells us we can just choose to prove the right disjunctive goal. So we got H here, entails P or Q. We start with the same outstanding sequence over here, the same. But we can choose to prove just Q. So this will be OR, R2, because this will be R2, you can think about, all right? This is like R1. Think of it that way. And that one there is going to be H, entails Q. Which one to really choose depends on your sequence look, right? So these are the rules that we need to understand, at least for another 1 or 2 lectures. We're going to introduce another set later. All right? And final one, monotonicity, we have seen that already. It's about dropping the hypotheses. Right? All right, any question? Why don't we take a very short break by taking attendance? After the break, we're going to talk about how to use these rules. Okay? All right, if you can get your mobile device ready, I'm going to pause the recording. Okay, so let's now do some more exercises. So before the break, we spoke about these inference rules. So take some time to really think about them, because later on, when you are facing a new proof problem, all you're given are these rules, but you need to know which one to apply, right? That's something you want to just get yourself familiar with the problem. Okay, and why don't we try right away, okay? We'll do one together, And then I'll give you guys maybe 3 minutes to try one of them, and then the other two maybe exercises. How about that? Okay. Why don't we do this one to start with? Oh, is this one the one we did earlier? Oh, this one we're already done. So how about this? This one here, let's not worry about. This one will be exercise. However, that's something we just did earlier, but I can redo it. Okay, let's now do something new. Exercise. All right. So why don't we try this one here together? Let me try this one together with you. All right. So let's say we're facing this, and I can tell you as a hint, these are the relevant rules you can use. You got ORR1. I'm even telling you it's ORR1. It's not even ORR2. And you can use monotonicity. You can use the decrement rule. You can also use P2. Okay? How do we go about this one here? Well, we're going to apply the similar principle that I mentioned earlier before the break. Because right now, what we want to prove is this guy here. N minus 1 is a number of natural number. Right? So we know that what's really relevant here is N. So this guy, not relevant. It's about D. And since we are going to decrement N, whether N is less than or equal to D may not be so relevant. So it turns out only this one here is more relevant than others. Okay? So what I will do is I'm going to apply monotonicity right away to drop the hypotheses. So I'm going to just say I want to keep this guy here. I want to keep it. And the rest should be dropped. And when you apply the monotonicity rule, you don't have to say explicitly which one to drop, because whatever that's left implicitly tells you which one has been dropped, right? So what I will do is I'm going to have monotonicity here, and then I'm going to have a new sequence that's more compact. N is a natural number entails N minus 1 is a natural number. Guys, how does this sound to you? I want to pause over here and tell me what you think. This one is really worth thinking about. Go ahead. Yeah, exactly. You're already thinking about counterexample, right? So this one here overall should not be provable because you can find some counterexample, right? So this one here should not be in general provable. N is a natural number doesn't really imply N minus 1 will be a natural number always, because as you said, if N is 0, in that way 0 minus 1 is definitely not a member. Good? That's very nice. So these are unprovable. We need something else. Unprovable. So this is a critical thing. In 1090, when you reach this step, you're basically done. To say this sequence here is unprovable, right? But now in this course, you're not done. You're only halfway. You're actually going to now interpret this sequence here and see what should we do back to the original model to fix it. Here is what you want to think. Number one, how did we arrive into this unprovable sequence? It comes from this particular proof obligation. This proof obligation has to do with the MLN. And it has to do with invariant condition number 1, which is over here. And the nature is about invariant preservation. All right? But now it's unprovable. Something is wrong. Especially if you look at MLN. Let me remind you very quickly. If you look at the rule, that one tells you, the rule tells you should really include the guard of the events. But somehow ML out has no guard. It will be as if it's always enabled. So it's as if we put true over there. Okay? So if you go back there, to this unprovable sequence over here. So this one tells you what you put originally, you'll be as if we got some true over here. And the true here is the guard of MLN. The true here is simply too weak. It would be so nice if we can add something over here as an extra hypothesis so that this sequence over here can be provable. You see what I'm doing here? I'm basically moving between math and the model. The math is really there to help us get some insights into our model, because our model is more like a specification with all the predicates. And somehow we turn the model into individual proof sequence over here, but the proof sequence cannot be shown provable. So that's why we got to go back to the model itself and see what can we fix the model. And in this case, what it turns out is this. Guys, please. Thank you. Okay, so now this is something we want to add. So one possible resolution is to add some guarding condition of MLN. We're only talking about MLN. MLL is not relevant right now. So that the extra hypothesis can make this sequence provable. So this is a very valuable lesson for us, because we're not just trying to do some symbol manipulation for sequence. It's actually a tool to help us understand our model. That's really what one of the main messages for this course, right? All right, so let me highlight it, and then we got about 5 minutes. I'll try to see what we can do. All right, over here. Any suggestion? Oh, so many, good. Okay, why don't you go ahead. And bigger than 0, I agree. And I wouldn't say conjunction though, because when you add some extra hypothesis, I wouldn't say, for example, maybe what you meant was you want to say this and larger than 0. I wouldn't do that. I would rather put it as a new line and put n larger than 0, just in case we want to drop maybe this guy here as well later. Okay, just for now. All right, that one I agree with you. Okay, guys, you can think about whether you're convinced. Here could be n larger than 0. All right, so this is something we're going to reference to on Thursday when we come back, but let me take a few more minutes, and then I'll let you go. Give me 1 moment. Okay, this will be the new guard for MLN. And I'll suggest we do one more. Yeah. And before that, question, please. Yes, question. Oh, so when we say we add a guard, so I'm simplifying some steps over here. This is what I meant. This might be nice to clarify. Conceptually, we have our M0, which has the static part, also dynamic part, right? The model and the context. That's what we start with. And then, based on the model, we generate a set of proof obligation. Proof obligation rule tells us we can generate ML out, invariance 0, 1, and then IMV, etc. And then, once we have generated them, for example, let's say this guy here. Oh, the one we had was MLN. Let me just make sure I refer to it properly. Also, MLN, invariance 0, 1, invariant. Let's say, for example, this one here, what we do is we try to prove it, attempt. to prove it. And then we arrive in a sequence that's unprovable. Something that's unprovable. By the way, if that's provable, we are done, right? That's unprovable, which is this guy here. And what we are doing is we are basically go back to the model over here and fix it. The way we fix the model, so let's number the sequence here. Number 1, based on the proof obligation rule. Number 2, we attempt to prove it. Number 3, we try to fix the model. And when we fix the model, we're basically saying here, so number 4. So for your ML in, and then we're going to add the guard over here. Rather than no guard, we're going to say n larger than 0, and etc. So now, this new guard is going to trigger new sequence to be proved. And number 5, we're going to regenerate all the sequence. Once we regenerate all the sequence, what we're going to see is this sequence over here is now going to contain n larger than 0 as part of its hypotheses. That's what's going to happen. Make sense to you? Yeah, I think this process here is really important for you to remember. That's the process. We don't just arbitrarily change the sequence we want to prove. That'd be too good to be true, right? We cannot do that. All right, guys, I would suggest you guys try this one here and also this one here before Thursday. All right, and then we're going to continue from here, and then we can move on to fixing the model and reproving it. All right, I'll see you on Thursday. And don't forget for tomorrow for Lab 4.